Welcome back. We are looking at cellulose, which we said that cellulose as a polysaccharide is not one polysaccharide chain, but rather tens of thousands of polysaccharide chains link up together by hydrogen bonds. So we can look at another polysaccharide called glycogen. Some books even mistake it and say glycogen is animal starch. But that is just to say what it does. That glycogen is a storage carbohydrate. In animal bodies. For instance, when you eat a lot of starch from plant materials, you digest it, starch is digestible, you digest it into glucose units, subunits. When you absorb that glucose, some of it you will use it from energy, but the excess glucose is converted into glycogen, then stored in your tissues. So glycogen, that's why it is called animal starch, because they are sharing a function, the main function being that starch is a storage carbohydrate and also glycogen is a storage carbohydrate. So to start large, in our bodies as animals, we do not contain any starch, but rather glycogen is one which we contain as a polysaccharide chain. So how does it look like? It consists of one alpha glucose units. So when you digest starch, absorb it from the ileum into your blood, the excess of it, the excess alpha glucose is converted into glycogen and stored. Then it is branched. It is a branched chain. Could that be a chain more? It is a branched chain. So because it is branched, glucose is bonded by 1,4 and 1,6 glycosidic bonds. One 4 and 1,6 glycosidic bonds. So within the glycogen molecule, the branches are there. So, which polysaccharide have we said that the branches like that? The polysaccharide amylopectin, a form of starch, is also found in branched to this level, but only that glycogen over branches. It has very many branches, but the properties in terms of bonding between amylopectin and glycogen are the same. So at this junction, that's where we're going to find the 1,6 glycosidic bond. Then in the continuous chain, it is 4 glycosidic bond. So it goes like that. It goes like that. So the glycogen and amylopectin share a lot. They share a lot. Alpha glucose units, branched chains, and even 1,4-glycosidic bond. So now we can see the polysaccharides. Those will be our common polysaccharides: glycogen, starch, and the amino and glycogen. So now we can take a hand and compare comparison between cellulose and starch. Between cellulose and starch, sorry for that. Between cellulose and starch, we would begin with the similarities and see are these molecules similar in any way? Similar it is. One, what could be our main similarity? At least that both contain 1,4-glycosidic bonds. 1,4-glycosidic bonds. Both being polysaccharides. So we can now say both are insoluble in water. All polysaccharides are insoluble in water, so both of these are insoluble in water. We can also add on and say that both consist of repeated monosaccharide units. Repeated monosaccharide units. Very many of them repeated to form a chain. So they consist of repeated polysaccharide units. What are the differences between these two molecules? Between these two molecules, we use a table form to represent my differences between these two molecules, that is starch and the cellulose. These two molecules have something in common, but they are different. At least we can begin with the sugar units. That is, starch consists of alpha glucose units. If it consists of alpha glucose units, this one consists of beta glucose units. That's one difference. The second difference can arise from the kinds of polysaccharide units that are within these molecules. We know that the starch has two different polysaccharide units. Polysaccharide units. We have seen that in cellulose consists of only one type of polysaccharide chain. One type is present in cellulose. So meaning cellulose also has no, this starch now has no cross linkages between polysaccharide units. This has what? Has cross linkages in between polysaccharide units. Then lastly, we can take the functional difference and we say starch. Starch is mainly for storage and cellulose mainly for structure support. That would be the comparison between these two, between starch and cellulose. So briefly, that the kind of bond can help us distinguish these molecules, the kind of monosaccharide units, the kind of we can even include the branches and whatever in our comparisons. That is starch compared to cellulose, compared with cellulose. So how does cellulose get that power to give structure support? We talked about it and said that cellulose has a lot of cross bridges. Those cross bridges make cellulose very, very tough, that it can withstand mechanical stress to support plant materials to the level that we can sit on them and they do not break. We can continue and compare. If we compare comparison between glycogen and starch. Comparison between glycogen and starch, we also begin with the similarities. At least we know that both consist of alpha glucose units. So if both consist of alpha glucose units, and also we can say both consist of repeated sugar units. The sugar units are repeated in those molecules. We can also say both are insoluble. Both are insoluble in water. And we can give a functional similarity and we say that both are storage carbohydrates. Both are storage carbohydrates. That is the functional similarity between these two molecules. So we can go to differences between starch and the glycogen. As usual, it is better to tabulate our differences. So there are very many methods of representing the differences, but majorly in the table it looks better. So starch compared to glycogen. What would be our first difference? The first difference would be in kind of bonding that is present in this. We say that starch consists of hydrogen bonds. Hydrogen bonds in amylose. Glycogen lacks hydrogen bonds. Lacks hydrogen bonds. Then we can go to the branching. We say that starch consists of two different different chains. Consists of two different chains, whereas glycogen consists of one. It consists of one chain. The other difference would be the functional difference. That starch is a storage carbohydrate in plants. This one is a storage carbohydrate, in animals. It is a storage carbohydrate in animals. So because of this, we can now compare these molecules. We can compare these molecules. So that is it. So we are winding up with the carbohydrates. So we can now say carbohydrates are diverse. That is, carbohydrates are diverse. Carbohydrates are diverse. What would this mean when we say carbohydrates are diverse? It would mean that there are many forms of carbohydrates that do exist. So meaning we can now say ranging from monosaccharides Monosaccharides, we have very many examples, such as glucose, fructose, even ribose. That's diversity. We saw how monosaccharides are very, very diverse, ranging from carbonatom number 3 even to carbonatom number 10. Some even contain 10 carbonatoms in them. Then going to disaccharides. So there are more disaccharides. We know that maltose is there, sucrose is there, and then 3 up to when we have come to polysaccharides, where we have found starch, glycogen, and the cellulose. So that's how diverse carbohydrates are. So we can wind up with this summary about carbohydrates, and in our next session we shall discuss other chemicals of life.